In this video, we're going to delve into some maths and explain what radians are. And then we're going to get into some physics and explain what circular motion is, specifically uniform circular motion. So it is possible that you don't know the concept of radians, but that's okay. It is quite possible that in your school life that you dealt with angle problems in the measurement system of degrees, such as this angle being 180 degrees. But there is another type of measurement, and it's fairly easy to understand, and quite handy in a lot of different situations. So even though this is a quite bad drawing, let's say this is a circle, and we define a unit of radian like this. A unit of radian is defined as 1 radian when the length of the radius of the circle is equal to its arc length. That's defined as 1 radian. And it is important that you should know that the whole circle angle, which would be 360 degrees, is equal to 2 pi radians. With the same logic, you can say that 180 degrees is pi radians, and 90 degrees is half a pi radians, and so on and so forth. In most cases, dealing with angles in this manner helps us quite a lot. That is why you should also get used to studying with radians when you're studying trigonometry. So now we deal with that. Let's understand what circular motion is. So we covered the topic of linear motion in the previous videos, where there is only a stable direction of the velocity of the system. But what if the angle of this velocity is changing? In such a manner, what if it's changing as if it was going along a circular path? What is going to happen to our velocity in this situation? Well, in each time frame, we'll see that our velocity is perpendicular to our radius of our circular path. And if the magnitude of the velocity, or to say our speed, stays the same, but only the angle or the direction of the velocity is changing, how do we define that? Well, there needs to be some kind of acceleration here, because from what we know from the previous videos, that acceleration is defined as a change in velocity. But a change in velocity doesn't always mean a change in magnitude. But where is this acceleration? What is the direction of it? Well, if you think about it for a little, you'll see that the acceleration is always perpendicular to our velocity. It makes sense when you think about it because that it is perpendicular to our velocity. You can think of it as like in every time frame, every tiniest time frame, the direction of our velocity is always knocked a little bit off to the side. And if our acceleration is perpendicular to the velocity, the direction of our acceleration never changes, but it follows the path of the velocity. So it's always pointing at the center of our circular path. That is why on each new time frame, our acceleration has changed too. And it changes the velocity for the next time frame just by a little amount. But what is that little amount? Well, we can calculate it. So, first let's look at how our velocity is changing. Let's say this is our initial velocity and this is our final velocity. The difference between those gives us a change in velocity. And in a graphical manner, we can represent it as such. This is Vi and this is Vf. To substitute this, let's give this Vi a little negative sign and change its direction. Now, if we add these together, we'll see that this is a resulting change in velocity. But how do we calculate this? Well, follow along with me for a little. So we know that this is our radial vector, and it's always the same along this path. We can say that this angular value here is theta. And we know that the relationship between the radial vector and our velocities is such that they're always 90 degrees apart. Meaning that the resulting triangle made from the change of velocity and the change of radius is the same. Well, not the same, but they're similar triangles. So they have similar ratios. That's why we can say that our value of change in velocity to our initial velocity is equal to the value of change in radius to our radius. That's our starting point. Now, for our second move in our proof, we know that our acceleration is equal to our change in velocity divided by the change in time. And from here, we can substitute the change in velocity such as v times the change in radius divided by r times the change in velocity. The change in time. We know that the change in radius divided by the change in time is equal to our velocity. So we can say that our acceleration is equal to v times v, which is v squared, divided by the radius. This here is defined as the centripetal acceleration. And in every uniform circular motion problem, you will be dealing with this. So you should know it by heart. Now, what if our path wasn't completely circular, but changing depending on the time? In that case, we know that we have to deal with our problem by a bunch of different time frames. Let's say that we have our particle here, and it starts with a velocity in this direction. But in time, it follows a kind of unpredictable path. And the velocity, direction of the velocity is different in every single frame. And supposedly the magnitude too. How do we deal with that? Well, like we did before, we need to define our acceleration first. But For this instance, our acceleration can't be defined just by the centripetal acceleration. Now we have to divide it. We can divide it into two different values, one called the tangential acceleration and the other radial acceleration. Radial acceleration is basically the same as the centripetal acceleration, but with a sign change. And it is fairly simple to see, because that every movement we take in this path can be defined by small sections of different circular motions. And for all of these different circular motions, we have different origin points and different centripetal acceleration for them. The sign for our definition of radial acceleration is the negative of the centripetal acceleration, because of the fact that the vector from our origin point to our trajectory is defined as the radial vector, and we take that as positive because that it is in the opposite direction of the radial vector. We define it as such with a negative sign. We didn't care about that while we were calculating the centripetal acceleration. The other part of it is the tangential acceleration, and this defines the change in speed, or such as the change of magnitude in velocity. But I'm not going to get deeply into that. That doesn't have a famous formula that you need to remember. The only way to define it is to just take the difference in speed and divide it by the difference in time. And that's our tangential acceleration. That is how we define non-uniform circular motion.